Hello everyone, this is Pradeep Rajasekar from Team Crow, and this is our final project for building deep learning applications coursework. And our project title is Image in Painting with Debluring and Denoising using GAN. And this is a two-person team. Myself, Pradeep Rajasekar, with Apoorvika Sukanthakumaran. We both equally contributed in this project from core to core. And this is our outline for this presentation. We divided this presentation into two main categories: architecture and then the implementation. And respectively, I will present and discuss the architecture, whereas Apoorvika will explain the implementation parts. As per our arrangements, I will start with an introduction and then the dataset we are used for this model. Then I will present the architecture of our network, and the later part will be discussed by Apoorvika. So the computer vision gaining much more traction in data science, and both lower and higher level problems of image processing took an interesting turn by a lot of new deep learning techniques. So we are approaching the lower level problems like inpainting, deblurring, and denoising with a GAN and autoencoder networks. GANs are basically a zero-sum game between two neural networks, which both are generative models. But before moving into the techniques, let me give a quick explanation for the problems we are addressing. First one is inpainting, which is basically an image completion where the given image has a missing or a damaged part, and the network has to fill it without knowing a actual missing part. Remember, the work here is to fill the missing area visually coherent and semantically appealing, not always exactly replicating the original image as it is. And deblurring and denoising part is self-explanatory, and most of the approaches or deals with these problems independently, and most of the time in-painted images suffer from noise and blur while producing the missing region. But our model could take an incomplete or damaged image and fill it properly, then denoise and deblur the image. And our model optimized for face completion, and the dataset we are choose is the infamous Celebi dataset, which has tens of thousands of high quality images of a human faces. Celebi has large diversities and quantities and rich annotations, including large pose variations and background clutter. It has total over 200,000 images from little over 10,000 identities. And to train our model, we randomly split 162,000 images for training and 40,000 images for testing. And our proposed architecture. Our model contains two networks. One is GAN, which is in-paint the image, where the deblurring and denoising done by the stacked convolutional autoencoder. Even though there are two networks in the model, both are connected in a way that each will update the weights and parameters depends on the loss of the other network and act as a one. And that's our model's novelty. So the input image pass through the GAN model, where the generator and the discriminator works in adversarial mode, where the generator fills the missing region and the discriminator evaluates the integrity by comparing it with the original. But here we are optimized the GAN for inpainting purpose by introducing two discriminators. Instead of just only comparing the complete image with the original, it also separately compares the newly generated part with a corresponding original part of the image. After the image has been completed, the deblurring and denoising network take the completed image as an input and deblur it. To achieve that, we proposed a gradual training method with phase 1 and phase 2, where the phase 1 just GAN network in trained, and in phase 2 both pre-trained GAN and the deblurring network trained together. The training method is also one of our newly attempt, and this will be discussed later by Apoorvika. And as per our both network, each are optimized for our task and both will have its own architecture. And let me explain one of them. But before that, just a quick recap. The input image will go through the GAN, where the GAN is trained in the phase 1, And after the GAN is completely trained, that will the generator is pre-trained, and that will work together with the deblurring and denoising network and produce the output image. So the GAN architecture. We optimize the GAN model for in-painting method with two discriminator, both original GAN and deep convolutional GAN, I mean the DC GAN, are originally proposed for data augmentation and pixel-to-pixel translation. But for the image in painting, the both generator and the discriminator need to be optimized to complete the task efficiently. So as of the generator, instead of starting from the pure noise, we gave an incomplete image as an input to the generator. And as per the GAN network used in this model is adopted from the research paper globally and locally consistent image completion, and we are given credit to them. The citation will be given in the reference section as well. We used bottleneck architecture with total of 16 layers in the generator, where the 8 are convolutional layers and the remaining 8 are deconvolutional layers. And as you see in the picture, some of the consecutive convolutional and deconvolutional layers are exactly same in dimension, which ideas proposed and proven by VGG16 approach that using the same dimensional convolutional layers next to each other, the model can obtain a better understanding of future extraction and segmentation. And that's what we are tried to. But the discriminator had the big change. Since in inpainting most of the images from the generator is same as the original because we only try to fill the missing region, the difference measured between the created image from the original might not be the proper measurement for the loss function. So we add another discriminator which only evaluates the newly generated image with the original, that we called the local discriminator. So complete image evaluated in the global discriminator, where the generated region evaluated in the local discriminator. So the overall process is the incomplete image comes as an input and the generator completes the image with a bottleneck process. Then the completed image going through the global discriminator to evaluate its global coherent of the image, and the generated region will be evaluated in the local discriminator with its correspondent original. The loss from the both discriminators are back propagated to the generator to make it better until the generator outperforms the discriminator. Finally, we can get a trained generator which is capable of filling an incomplete image. And remember, after training the process, the discriminator will be suspended because there will be a no original image to compare. But the generated image may have blur or noise where the area is fixed, and that's where our deblurring and denoising networks comes into play. And that will be explained by my teammate. So from here on, Apurika will take on to discuss about the remaining process. Thank you, everyone.
Hello everyone, I'm Apoorvika. I'll continue with the deblurring and denoising network. This is our overall proposed deblurring and denoising network in our architecture. So let's see in detail. So this deblurring and denoising network is connected to the generator of the inpainting GAN. As you know before, it takes the generator output image as an input and estimates the cleared image as an output. So the structure of this network is a deep convolutional autoencoder with skip connections. As you see here, there are two main parts in this deblurring and denoising network. One is encoder and another one is decoder. So here, as you see, this green part is an convolutional layer. Here in the encoder, we are having four different convolutional layers, except the first one. Other three are for having the batch normalization and leaky ReLU activation along with them. So similar to that, decoder is also having four convolutional layers, except the last one. First three are having the batch normalization and leaky ReLU activation. So this helps to reconstruct the clear image. The size of an convolutional filters used here was 3 cross 3. So this is our training method. This method was already given in the proposed architecture before we have seen this, but still we will see how we are training it step by step. Here we have proposed a gradual training strategy because the complexity in this network to handle multiple tasks at the same time was hard. So end to end training is difficult here to make the network coverage. Therefore, they have proposed for this gradual training to get the better results. So here, as you see, it was an overall single model, but they have having two different phases. So first phase was in painting GAN. So as you see here, the complete training GAN network to in-paint the damaged input picture. So in the GAN discriminator will be suspended after the network is trained. So the generator will be having the trained images. So those images from the generator is already capable of filling the incomplete images will provided to the deblurring and denoising network as the input, and which will be capable of back forward the gradient and update weights from the generator to get the better results as an output. So these are the results obtained from our model. uh, so these are the they have trained the model with two different types, like without deblurring and denoising network as well as with deblurring and denoising network, to see the difference, like how it is giving the results. So without deblurring and denoising network, as you see here, these are the input images for our model, and here they have created the holes. As you see here, for the training they have set some minimum and maximum value for the hole, for creating the hole. The minimum value was set to 48, and the maximum value was 96 cross 96. So it will be deform creating a hole by itself. As you see here, the minimum size was given 48 and maximum was 96. Here we are having a different size in a hole, so it creates different size of holes. And as a result, for the without this deblurring and denoising network, here if you see, the image is not clear, it was somewhat blurred. And here the reconstructed image is also blurred and not clear. And here if you see, somewhat there is some mistakes in the eye part and the nose part. It's not, the image is not so much clear without this deblurring and denoising network. So as parallelly, if you see the results for deblurring with using deblurring and denoising network, these are our original images. And after that it had created some holes. And if you see here, after this deblurring and denoising network, somewhat the images are clear, it's not too much blurred, and it was somewhat similar to the original image as you see here. So here also his whole eye was blocked, so it has created the whole part. It is not blurred, but somewhat it is matching with him. And here also the eye part was missing, and it had reconstructed it better than the deblurring and denoising network. So as a result, the training model was giving the better results with deblurring and denoising network. So here for training the model, they have set the apox of 3 lakhs, and the batch size was 16, and the input size was, the original input size from the data set was 480 cross 480. We have downsampled them to 160 cross 160, so that it will be easy for our model to train it. So these are the conclusion. Here in our work, we have improved the deep convolutional GAN model with two different discriminators. One was local and another one was global, to suitable for this inpainting process, and makes the generator gradient and weights to update by working with the deblurring and denoising network. So here we have created two different model into a single architecture to get the better results than the before done models. Our model was giving somewhat better results. So, and we have also proposed for gradual training method in our model, so it also gave some better results. However, when compared with efficient of this model, it was somewhat not that much too good because the computational power requirement was too high. It took almost 40 hours to complete the model to train, even though when we were using Google Colab and the GPU was Tesla. So according to our knowledge, maybe it can be more efficient than this. So in the future, we are planning to update the neural network model along with the skip connections, and implying the output dropout regularization to make it more better and efficient architecture. So these are the reference for our model. We have referred a lot of papers, and we have come up with our model. Thank you.